Okay, now that we've reviewed if you've taken Calc 3 or have been introduced to vectors, if this is the first time you've seen it, we haven't defined a product of two vectors, right? We've defined the sum or difference of two vectors, and we've also defined the product of a scalar times a vector. Now we want to introduce one product of two vectors. And I want to maybe motivate this just a little bit, as motivating as math can be, but at least it's something. So we know how to multiply two matrices, right? Let's say we have the two matrices 2, 8, -7, 5, 3, 5, 1, 6, 1, -2, 1, 9, 4, 0, 8, -3. I should have made these a smaller matrix for the example, but and then the second matrix is going to be 1, 2, -6, 1, -1, 4, -8, 3. Sorry, it's kind of sloppy in there. I hope you can tell what order or what entry goes where. 5, 0, or 0, 5, 0, 5, and then 7, 9, 3, 2. Okay, and we want to multiply these matrices together. And what were we doing, right? Well, we know this is a 4x4 times a 4x4. So the result is going to be a 4x4, right? And let's say the first entry, or the first entry in the first row in the first column, let's call that A11. And how did we get A11, right? Well, what we did was we took the first column vector. Maybe let me call this B sub 1. This here will represent the first column vector. If this was to be like matrix A times B, right? That's where B comes from. And to get the first entry, we took this first column vector and kind of, I was giving an informal description and saying, well, we just kind of place it on top of the matrix and then you multiply component-wise here, right? And so what we did was we multiplied this for the first entry, at least, you know, for the entire matrix, you have to run through every column times every row. And if we called this first row of the matrix A, like A sub 1 here, then what were we doing, right? To get this entry, well, it was the first component of A1 times the first component of B1. So we had 2 times 1, and then plus 8 times -1, plus -7 times 0, plus 5 times 7, right? And so if you think about this column vector of B and this row vector of A, really what we've done is we've taken the product of the first component of A1 and B1, right? And here it's the same thing, but for the second, right? And for the third, it's the same, and for the fourth. Well, what we're doing here, this isn't just arbitrarily chosen. What we're actually doing here is we're multiplying two vectors in a certain way. We're taking the dot product of these two vectors. And let's see what the dot product of a vector is. And then I'll come back and compute the dot product of these two to see that what we did was just take a dot product, right? So here's a formal definition. The dot product of two vectors. Let's say we have U is U1 through UN, and V, which is V1 through Vn, is, and we write this as U dot V, hence the dot product, right? That's why we call it the dot product. We have U dot V is equal to U1 times V1 plus U2 times V2 plus et cetera, plus UN times Vn, right? And you can really see here, we're taking the first component of U1, multiplying it by the first component of V1. We add that to, right? You're taking the sum of products of components here. If you would like to see this written a little more compactly, the definition of the dot product would be the sum from I ranging from 1 to n of ui vi, right? And notice, it's really important to notice here that the input, this product takes two vectors, right? And the output is a number. This is going to be a real number, i.e. a scalar. And so the dot product, if you think about the dot product as a machine that takes inputs, and based on those inputs, it spits something out, or it gives you an output, the machine eats two vectors and spits out a number, right? And for this reason, the dot product is also called the scalar product. If you take more proof-based math courses, this will be called the inner product. But for this course, we will most likely only refer to it as the dot product or scalar product. Some notation here, this u dot v, let me just say some notation. U dot v can also be represented as uv in parentheses here with a comma separating them, or these angle brackets, uv. So if you ever see this notation here, don't let it throw you off. This is still just dot product or scalar product or inner product, right? These are synonymous in vocabulary and also in notation here. Cool. So if we had the vector 1, -1, 0, 7, so let's look at an example here. U is 1, -1, 0, 7. And then this was our B1, right? And then A1 was 2, 8, -7, 5. But let's take that transpose, right? So 2, 8, -7, 5. And really, this was our B1 in the matrix multiplication, and this was our A1 transpose, right? Well, then what would U dot V give us? Well, that would be 1 times 2 plus -1 times 8 plus 0 times 7 plus 7 times 5. And if you look, that is exactly this expression here. So really, when we're doing matrix multiplication, we're just taking the dot product of all possible pairs of vectors, like column vectors of B with row vectors of A, to be more explicit, right? And so maybe this helps with intuition for matrix multiplication. Maybe it's not so arbitrary that we just like picked this column and then that row and then that column and then that row. No, what we're doing is we're going through the dot product of all possible pairs here, and we're doing it methodically. So now that we know what the dot product is, and we've seen an example and kind of a retroactive application to matrix multiplication, let's look at some properties. Okay, we have that the dot product is commutative, meaning u dot v is v dot u. And as I'm going through these, with this one, can you prove this? I would like to kind of, I can't really assign this, or I am not assigning it, but an assignment for no credit would be to prove this. If you can, I would say you really understand a statement if you can prove it, right? And sure, we understand commutativity, right? We know A plus B equals B plus A. Like, we understand what that means, but what does it really mean in this context? Like, what does it mean to switch the order of the dot product? So maybe with some of these properties, see if you can prove these. Not all of them are trivial. The first one's not too bad. The second one here is saying that the dot product of a vector with itself is non-negative. So we have u dot u is greater than or equal to 0, and we have u dot u equals 0 if and only if. Remember, when I write two F's here, I'm not crazy. It's if and only if, meaning both statements imply each other, right? So they're it's an equivalent statement. This is if and only if u equals 0. We also have kind of a linearity property here. So let's say we have a scalar k times u plus a scalar l times v, and then we're taking that with the dot product of some other vector w. Well, basically what we have is that the dot product distributes. So this would be ku dot w plus lv dot w. But then we also have this kind of the extension of this property is that you can pull this scalar out front. And so this is k times u dot w plus l times v dot w. And we get an identical statement on the opposite side of, like if we put the linear combination here, if we put that on the right side, we get an identical statement. And that shouldn't be too surprising because we've proven by now that the dot product is commutative. So just for the sake of completion here, we have u dot, and let's say kv plus lw. This would be k, and I'm skipping this intermediate step here. This would be k u dot v plus l u dot w. Okay, let's see what else. We also have this kind of last property for now is a relationship between the magnitude or length of a vector and its dot product with itself. And so what we're saying here is that the dot product of a vector with itself is the same as the magnitude squared. Let's prove that one. Maybe I'll set a good example. Let's prove this one. So here's a claim, right? The claim is that the magnitude of u squared is u dot u. Okay, well, let's start with the magnitude squared. So proof. What does the magnitude mean? Well, first, let's define u to be the following vector, u1 through un. Okay, then what is the magnitude of u? The magnitude of u is square root of the sum of the components squared. So we have u1 squared plus u2 squared plus et cetera, plus un squared. Well, this would imply that if we square both sides, this gives us that the magnitude squared is u1 squared plus u2 squared plus et cetera, plus un squared. But if we want to be a little more specific about what the square of a number means, it means, well, that's u1 times u1 plus u2 times u2 plus et cetera, plus un times un. But by definition of the dot product, that's u dot u. So QED, right? And so this would be an example of proving one of these relations here, right? And now we don't just take this for granted and say, okay, the book told me it works, so it works, great. You'll have a much better understanding of this stuff if you try to go through this, right? And so if you want, and I would strongly suggest, try to prove these. All of these can be done by the same kind of argument here. Well, you just write out what the components of u are, right? Or write out the components of like v and w, and then you unpack the definition, right? You start on the left side of the equality and you try to take as many steps until you get to the right-hand side, right? That's what I did here. I started here and I needed to end there through a string of equalities, right? And I did that here. I started here and ended here. And so a similar sort of technique will work for these kinds of proofs. Okay, let's look at some really important theorems, and the proofs of these theorems. I would love to include them. They're a little lengthy for a lecture video at this level. So what I think I'll do is, if you're interested, you can read the proofs because they're pretty interesting constructions. But these are pretty significant theorems here. This is due to Cauchy and Schwarz. Whoops. Get out of the way. And this is the Cauchy-Schwarz inequality. And this says the magnitude of u dot v is bounded above by the product of the magnitudes. Okay, so this gives us another relationship between the dot product and the magnitudes of vectors. And I want to say equality holds if and only if u and v are a scalar multiple of each other. Okay, so you only get equality in this this equation here if they're parallel, basically. We have another theorem that's very important called the triangle inequality. The triangle inequality, well, let's look at what this says. Let's start with the triangle. And let's say we have side lengths A, B, and C. And we want to get from point P to point Q in two paths along this triangle, right? Let's say we start with the following path. First, we go along the side of length A and then the side of length B, right? And so the distance we traveled is A plus B. Well, then if we take path C, we know the shortest path between 2 points is a straight line, right? And so for that reason, we can immediately deduce that C is less than or equal to A plus B. This is the triangle inequality. Now, how could we phrase this in vector language? Well, let's say the base here, let's say that's a vector u of length magnitude u. The right side there is a vector of length magnitude v. And what would the hypotenuse length be here? Well, if you'll notice, the hypotenuse is the vector u plus v. And so the length of that is the magnitude of u plus v. And what the triangle inequality is stating here is that u plus v can never be bigger than magnitude of u plus magnitude of v, right? This over here, this was intuition. That certainly wasn't a proof. You need to be much more rigorous in a proof, but hopefully that gives us some good intuition. And again, equality holds if and only if u and v are scalar multiples of each other for some non-zero. So for some, non-negative, or not even non-negative, strictly positive. Sorry, I'll get there. So we also have with the triangle inequality a similar statement for subtraction or for the difference. We also have magnitude of u minus the magnitude of v is less than or equal to magnitude of u minus v. Okay. So I think what I'm going to do is stop here. And then in the next video, what I'm going to do is look at kind of the geometry of the dot product. Like, let's get some more geometric interpretations of what we're doing here, right? This is all very geometric because we're talking about vectors in space, and we can map these out. But what does the dot product mean geometrically, right? We know, we've seen, well, just here from this intuition, we saw again, what the geometric interpretation of the sum of two vectors is. And so in the next video, we want to get a geometric interpretation for the dot product, and then we want to see how we can use this. And so I'll start the next video by going through the geometry of the dot product, and then a couple applications or a couple concepts that we can build using the notion of how the dot product behaves geometrically.